All right, hello everyone. Welcome to week 2. All right, calm down. I'm starting the lecture now. I'm starting the lecture when everyone finishes their conversation. Okay. It's nice to see you. I don't mind everyone saying hi. It's not a big deal, but I am going to wait till you finish rather than trying to talk over you. So, week 2, hopefully by now you've all been to your tutorial class, you've met your tutors. Next week I will start to drop in on different tutorials, so you'll have a chance to chat to me at points throughout the semester. So a couple of minor things that arose. The first thing is I am aware that the lecture recording cut out halfway through the Thursday lecture and then restarted again. The incredibly silly reason that happened is because the Thursday classes are timetabled as 2 one-hour classes back-to-back rather than a 2-hour class. I spent a shocking amount of time on the phone to AV this week to get that fixed, and hopefully I found a workaround. So that shouldn't happen again. The bad news is those 5 minutes are lost to the ether. I promise you, if you weren't in the lecture, I was hilarious, but you'll never know. The second thing is, if you go to your allocate timetable, you will see that your seminar allocation for week 7 and week 11 have been removed, and you have been put into an assessment allocation. That allocation tells you where you need to be come the mid-semester exams. We don't need to worry about that for a while. I'm just telling you that now so you don't get too confused when you go and realize there's something on your timetable that wasn't there before. The third thing, there was a bit of terminology I used a little bit loosely last week, and I just want to clarify it. Now, I used it loosely because mathematicians tend to use this terminology a little bit loosely in practice, but because you're learning this, I'm actually going to draw a very clear distinction between two things. And those two things are as follows: tangent planes versus tangent spaces. In mathematics, we basically use these things interchangeably, but in the course of this subject, I'm going to say that the tangent plane, for which we got this formula for, is a plane that touches your surface at a point P. And the tangent space is the set of vectors in the tangent plane. These are slightly different. This doesn't exist on the surface. It's just a vector space made up of all the vectors that are tangent to the plane at that point. This is actually an important distinction for the big reason that this is a vector space, which means that it has a 0, whereas this doesn't necessarily. And of course, you have all of the addition and commutative properties that vector spaces have. So nothing was wrong, but I did go through and touch up the notes to make sure that these were used in this setting, and we will use that going forward. So I just want to clarify that because it did cause a bit of confusion, and that was because mathematicians can be a bit lazy about terminology. I'm glad we got to the bottom of that. So just in case anyone was still a bit worried. But last week, we took things a bit abstract. We talked about kind of the most abstract definition of tangent spaces, and we started computing them for surfaces. What we're going to do is pull right back to something very concrete, and something concrete that I am certain you have all seen before. But we will be taking it to constrained optimization after that, which should hopefully be new to more of you. So we're going to start by talking about maxima and minima, or unconstrained optimization. If I give you the graph of some function z equals f of x, y, how can I find its extreme values, its maximum and its minimum? Now, we're going to be using second partial derivatives. So what we want is to say that f is at least C2. C2 is a shorthand for twice continuously differentiable. You might have seen it before, but I'm not going to assume anything at this point. Twice continuously differentiable. All of the second derivatives exist, and from the exchange of derivatives theorem we spent a lengthy amount of time proving last week, we know we can reverse their order. A quick side note about that result, by the way, for the next 2 weeks after this, we're going to do multiple integration, and that same theorem lets us switch the order of integrals as well as derivatives. I'll mention that again next week, but should mention that in passing. Okay, so basically this is just saying f is sufficiently nice. F is nice enough that everything I want to do, I can do. Okay, so we want to start by finding extreme values, things we call local maxima and local minima. And you're pretty familiar with this from certainly single variable calculus as well, but let's get the definition right for multiple variables. It's a point such that there exists some disk of positive radius around that point where f of xy is greater than or is less than or equal to the value at the point for all x and y in the disk. For all x and y in the disk. So if I have some point here, which is my x naught and y naught, then for this to be a maximum, I should be able to draw a disk in xy, and every point in that disk should have f of xy less than or equal to f of x naught, y naught. And that's exactly what we have. Basically, everywhere I go down. And you'll remember we learned about directional derivatives last week, so this is going to give us some insight into how we're going to tease this information out. And similarly, the definition for local minimum is exactly the same, except you change the direction of the crocodile. F of xy is greater than or equal to f of x naught, y naught everywhere in the disk. So here is our disk in xy. Here is the disk of positive radius around the point x naught, y naught. And every single point in that disk is greater than or equal to f of x naught, y naught. So a fairly natural definition, but a precise one, which is useful because precise definitions are important. Yes? It does, and we are still considering that a local minimum and a local maximum by this definition, although we're going to those are sort of degenerate cases that we will touch on briefly. Mostly the theory we're about to do breaks down in that case, so we don't lose too much stress about that. But yes, so for instance, there's a very classic result in complex analysis that if you have the only local maximum that is also a global maximum is the constant function. So you do actually want the equality in there for some tricky definitional purposes that will never be relevant to us. Okay, so let's prove a very important point. We want to say, and we're going to use this as the ammunition, the tangent plane, so I'm sticking it to that point. In this case, the definition doesn't matter. I could have said tangent space. At a surface, at a local maximum or minimum is horizontal. So what I'm saying is if my contention is that this is a local maximum, then the tangent plane at that point, which is, of course, the tangent space glued to the point, is horizontal. And when I say it's horizontal, what I really mean is that the normal direction is parallel to the z-axis. We're going to do a lot of this theory as we put it together and the derivations in 2 dimensions, but we will talk about n dimensions as well once all of the 2-dimensional theory is in place. And I didn't just draw this picture because it makes the page interesting. It actually gives us some intuition into how we can prove this. Because you see, if the tangent plane is tilted rather than flat, so if this is wrong, if that tangent plane could tilt, then there must be a direction where the directional derivative increases, because at least very locally, the directional derivative shoots off in the direction of the tangent plane. If they're all flat, that's kind of saying that all of the directional derivatives move horizontally first, and then will eventually go down. If that plane is tilted, some will start by going down, some will start by going up. That can't happen because if the directional derivative goes up, we have a problem. It's no longer a maximum. So you might think, why are we going to prove this? You've just given me kind of a hand-wavy justification as to why, and that's a good thought. Often when we present proofs in class, we just say, all right, here's the theorem, and now we're going to go through the steps that get us there. But we want to try and give you some idea of how we get through these theorems as well. So when possible, we'll try and motivate the theorem or offer a bit of a proof sketch so you can say, well, how could I have come to this conclusion myself? So, you know, this isn't the proof, it motivates the proof. So if the tangent plane is tilted, there is a direction where the directional derivative increases, which is what we don't want. And we don't want that. I meant to put that in at the end. So the directional derivative of our function f at the point x0 in some direction d, where I'm going to say d is a unit vector just to make the algebra a bit easier. We can always do that without any loss of generality. So we'll pick a unit vector d. I will try to remember to put hats on unit vectors. It's easy to forget that because that tends to be a teaching device, but I'll do my best, unless I decide I don't want to. There are cases when it makes things a bit messy and it's just easiest to remember that something is a unit vector. Okay, so the directional derivative of f in a direction d, and of course the direction is expressed in x and y. So maybe d is a vector here, like this. Is equal to, from last week, the gradient of f at the point x0, y0, projected onto the direction d hat, which, from first year, we recall, probably you learned in linear algebra, I hope, that this is absolute value of x0, y0, absolute value of d hat, which is 1 because it's a unit vector. Let's move this up here because I'm about to need that space. Which is equal to, oh, sorry, I forgot the cos theta. Cos theta, where theta is the angle between the two vectors. This is the norm of a vector. It's some positive number. This is the norm of a unit vector. It is a very specific positive number, 1, and this cos theta has values where it can be negative. So this has values where it can be positive or negative. There's nothing I can do to say that this has to only take positive values, because cos theta can be both. Since this must hold for all theta, the only way I can avoid tilting the plane is if this thing is 0. So the only way I can get a flat plane is if this quantity is 0. This is not 0. This is not 0. So this has to be 0. So the only way I can get a flat plane and thus avoid this thing going positive is if the absolute value of grad of f of x naught y naught, which is equal to the absolute value of f of x at x naught y naught, f of y at x naught y naught, is equal to 0. Which is to say, and the reason for this, in case you forget, is that if the absolute value of some vector v is equal to 0, then v is equal to the 0 vector. There's no other way to get that. You can't have stuff cancelling when everything is non-negative. Okay, so therefore, f of x is equal to f of y is equal to 0. So we now know that our tangent plane f of x is equal to fy is 0, which if we go back to our little definition of the tangent plane here, says that our tangent plane is just a constant value. So that's good news, and it also means that we can define our normal vector to be minus fx, x naught, y naught, minus fy, x naught, y naught, 1 from last week, although I moved the minus signs in front of the fx's and xy's, which is equal to 0, 0, and 1, because f of x is 0 and f of y is 0. So if I have a local maximum or minimum, then I have a tangent plane that is horizontal. We have not necessarily proven it the other way, but this is all we need. Proof, QED. The boxes are very satisfying. Okay. So we have maxima, we have minima, but this also suggested something very important in passing, which is the real thing to take away from this. So we construct this result by thinking about the tangent plane. But actually, this result tells us something incredibly important, which is that the norm of grad f is 0. And if the norm of grad f is 0, can someone tell me what grad f is? Anyone? 0, exactly. It's the only vector that grad f can be. Also, grad f of x naught, y naught is equal to 0. A very convenient result, and the one that we are going to use. However, we haven't shown that grad f being equal to 0 necessarily gives you a maximum or minimum. It's possible that there might be something else. So what we're going to do is define this as a critical point. A critical point is any point x naught, y naught, where the gradient at that point is 0. So that's the definition of the critical point. It's a very, very slight difference from a local extrema. A local extrema is defined in terms of the values of f. This definition doesn't care about the values of f at all. It's just saying the gradient is 0. What happens here? Well, that's up to you. And of course, what I think you know already, and what we'll certainly know in 5 minutes, is that there are a lot of different things that could happen. So let's illustrate this by, well, 3 different things. Let's not go crazy. 4. So, a theorem. We say theorem, I'm sure. Every local maximum and minimum is a critical point. In some sense, what we've just shown is that. And proof on previous page. So we already got to draw our square. We don't get to draw another one. We proved that already. There's going to be a little bit of this going throughout because the proofs that are informative, I will actually step through to show you why a result is true. In this case, we've already shown that to be the case because of this. Okay. We'll do an example because calculations are nice, and remind everyone that there's probably going to be an exam where you have to do a calculation at some point. So I've got my surface here, x squared minus y squared minus x to the 4. So that's my surface that I'm drawing the graph of. I calculate the gradient, and you also calculate the gradient. Take 10 seconds, calculate the gradient. All right, that's long enough. Hands up. Can someone tell me the first entry? Yep.
2x minus 4x cubed.
2x minus 4x cubed. Perfect. And can someone tell 4x cubed? And can someone tell me the second entry? Yep. Negative 2y. I will be doing this from time to time to make sure you're all awake. It's 9 a.m. and I don't blame you if you doze off. I'm sure you all had a big night doing homework. So, grad of f equals that thing. So we need to find our critical points, grad f of x naught, y naught equals 0. And I've drawn this picture, and we can see probably there's going to be 2 local maxima. So there's certainly going to be 2 critical points. It is just possible that this may also be a significant point. Let's see how that shakes out. fx has been calculated as 2x, I'm going to write as 2x naught, 1 minus 2x naught squared. And I'm going to say fy at x naught, y naught is minus 2y naught. So f of x equals 0 and f of y equals 0. There are 3 solutions to fx. We get x naught equals 0. We get x naught equals 1 on root 2. And we get x naught equals minus 1 on root 2. I'm not going to make you solve that. I'm sure you can all do that. And here we get one solution, even easier. Y naught is 0. So we see there are 3 points where both x naught and y naught are 0. Normally these won't decouple into x and y quite so nicely, but I didn't want to waste time doing too much algebra. So our critical points, and remember, this doesn't tell us anything about the critical points other than those are the points where the gradient is 0 and thus the tangent plane is horizontal. So we get 1 on root 2, 0. And minus 1 on root 2, 0. And that is this point and this point. And you can see it doesn't matter which direction I go from here, I go down. So these are clearly local maxima. But I also get this point 0, 0. And unsurprisingly, things are a bit different here. If I go in these directions, I go down. But if I go in these directions, I go up. So here I go up, and here I go down. This is not a situation that was covered by the result on the previous page. This is something you haven't seen in this slide so far. However, there's this nice box here at the bottom, which might have suggested what's going on here. This is what we call a saddle point, thus named because it is saddle-shaped. Your legs go there. I don't know. Has anyone ridden a horse? It's vaguely saddle-shaped. It's also Pringle-shaped, if that is a better analogy for you, as it was for me when I was a university student. A saddle point is a critical point x naught, y naught, such that any disk of positive radius contains some point xy, such that xy is greater than or equal to f of x naught, y naught, and also some point x tilde y tilde, such that f of xy is less than or equal to f of x naught, y naught. So again, excluding the degenerate cases with equality, you can either go up or you can go down, depending on the direction you choose. The more and more dimensions you have in your problem, the more generic saddle points are. We'll see that once we get to the classification theorem. But, you know, in 2 dimensions, you could be either. So up, down. And that's essentially every kind of critical point you could possibly care about. So what we're going to do is we're going to talk about classification, then I'm going to give you a 1-minute break, and then we'll pick it up. This is what I like to do in 1-hour lectures to keep focus. How are we going to decide? Classification is about deciding what your critical points are. The algorithm for finding a critical point is nice and easy. You get your grad of f, you solve it to be 0, it spits out some numbers, and then you load up Mathematica and you squint at it a little bit and you're like, that one's a maximum, that one's a saddle, that one's a minimum, that one's a weird degeneracy. But it would be nice to have some algebra because, as we learned last week, you can't always draw every surface you want to understand. The dimensions are too high, it's in some kind of field that doesn't lend itself to drawing. There are lots of reasons why we would like an algebraic classification theorem. So that is exactly what we are going to do. So in single variable calculus, this was very, very easy. We learned the second derivative test, which basically said, if my curve is going like this, it's a maximum. And if my curve is going like this, it's a minimum. But of course, in single variable calculus, those were the only 2 options. Here, there's other things that can happen. So a single derivative test told us that f dash dash of x naught was greater than 0. That meant that what we had was a minimum. And we learned that if f dash dash of x naught was less than 0, we had a maximum. And of course, we learned that if the second derivative was 0, it was inconclusive, because it was a weird degenerate edge case. For C2 functions, more than two variables, we need a little bit more things. We need to consider quite a few more things that could be going on. So we need to consider all possible second derivatives, and to do that, we need a way of talking about all of the possible second derivatives in fairly compact notation. And if you thought this class was missing linear algebra, you're about to breathe a sigh of relief. Because what we actually need is a special matrix called the Hessian matrix. Fx, yeah, right. Fxy, Fyx, Fyy, which has the notation H and is called the Hessian matrix, named after some guy named Hess. The Hessian matrix. Because we proved that we can switch the orders of derivatives, we can say that the Hessian matrix is symmetric. That's very convenient. Why is the fact that the Hessian matrix symmetric such a convenient thing? Tell your neighbor, don't tell me. So turn to your neighbor and speculate why the symmetry of this matrix is very important. There might be a sentence underneath that nudges you in the right direction. All right, wrap it up. And if you're feeling confident that the two of you putting your minds together came up with an answer that is correct, and maybe if you're lucky, the answer I'm looking for, put your hand up. Okay, if you're moderately confident that you came up with something correct and I have no faith that it's something I was looking for, yeah, a hand up. It does have a nice determinant. That is very true. It has a nice determinant, and it having a nice determinant means it has nice eigenvalues. What do we know about the eigenvalues of a symmetric matrix? Well, in 2922 at the very least, you will learn that the eigenvalues of a symmetric matrix are real. And that is a very convenient fact for us right now. So we will lay out an algorithm, and then I'll give you 30 seconds. Actually, no, I'm going to give you 30 seconds now. Just take a moment, breathe, collect yourself, and then we'll do some more linear algebra after this. 30 seconds. All right, 10 more seconds. Okay, good stuff. When possible, now that I have a better handle on the timings, I like to give a break in the middle just to let you get it all out of your system so we can power through to the end of the class. I will try and do that if we're not running behind as a general rule. Okay, so the algorithm we're going to follow, and we are going to prove this, at least for the two-variable case, is that we find the eigenvalues of the Hessian. Seems like a good place to start. Seems like everything here is linear algebra, and that is indeed the case. This is one of the reasons that it's so important we work in a tangent space, because we want to be able to use the linear algebra properties. In two variables, there are four things that can happen. Either both of the eigenvalues are positive, both of the eigenvalues are negative, the eigenvalues have differing signs, or at least one of the eigenvalues is 0. And what we are going to find is that if both of the eigenvalues are positive, that means we have a local minimum at x0, y0. If both of the eigenvalues are negative, that means we have a local maximum at x0, y0. Now, these are, of course, both what you found in the one variable case, because the Hessian for one variable is just the second derivative. So this is, for one variable, just the second derivative test. But because we have two, we can have eigenvalues that are differing signs. And that means that we have a saddle at x0, y0. And because nothing is ever easy, we also have the inconclusive case when any of our eigenvalues are 0. In n variables, this extends quite naturally. If all of your eigenvalues are positive of your Hessian, however many dimensions, however big your Hessian is, so for the Hessian, you have, well, we'll do this one in a bit. For n variables, if all of the eigenvalues are positive, it's a minimum. If all of the eigenvalues are negative, it's a maximum. If you have any kind of sign change, it's a saddle. And if any of them are 0, it's inconclusive. So exactly the same. And we'll actually do a 3-variable case as an example later on so that you can see the right construction of the Hessian. The proof just comes from Taylor approximation. It's not altogether that fancy, but it does require some stuff that you might not remember from multivariable calculus, and in particular, how to construct a Taylor expansion in multiple dimensions. It's possible that you did this in a sort of hand-wavy way, but without linear algebra, this is something that you can't really do. So, to sketch out what we're going to see, we're going to start with what the Taylor approximation of a multivariable function is. So here I've written f of x plus h, but x is a vector, so you can think of that as xy or xyz or whatever you want. And h is also a vector, so it could be perturbing any one of the variables or more than one of the variables. Is equal to f evaluated at x, where remember, x is a vector, so that could have a lot of multiple variables, x and y. The gradient of f at x dotted with my perturbation h. This is kind of like the first correction term to a Taylor polynomial, which is the derivative of f times by x minus x naught. Sorry. Down the wrong way. All right. Sorry about that. But the next term, a little bit more complicated than your standard Taylor polynomial in one dimensions. You've got the half, or the 1 over 2 factorial, so that's nice. Then you get h transpose times by the Hessian times by h plus order h squared, which means everything that's left is smaller than norm of h squared in the limit that h goes to 0. Or, have you met big O notation before, or is this new? Okay, good, you've met big O. I taught a 4th year class last semester, and half the class looked at me like they had no idea what I was talking about. So, big O notation. All right. Quick definitions, because this is going to be very useful. And this is something you might remember or might learn in 2922, but we need to very quickly discuss what it means for a matrix to be positive definite or negative definite, because it is relevant for reasons that should become apparent. So if for all v, any v you choose, v transpose AV gives you a positive number, then A is what we call positive definite. Whereas, if for all v transpose AV gives you a negative number, then A is what is called negative definite. These are very useful traits. The reason these are useful, as you might imagine, is this will eventually manifest in saying that any direction I choose to go in will have a positive gradient, or any direction I choose to go in will have a negative gradient. But we need to do a bit of work to get there. We don't get that for free. What we do get for free is that if the Hessian is positive definite, what that means, and what we can take as a given, is that all of the eigenvalues are positive. That is where positive definiteness comes from. If H is negative definite, then lambda j is less than 0. Okay, so this is nice. It's not the whole proof yet. Obviously, it's not a proof. This is a proof sketch, but we will do this properly. We're at a critical point, which means grad of f of x is equal to 0. Critical point. Makes sense. That's how you derive the second derivative test in one variable as well. So we've got some constant thing, which is the value at our point, plus this thing here. And in some sense, h can be any perturbation we want it to be, because the choice of h just tells us in which direction we're going. If this is positive definite, then it doesn't matter what h we pick, this is going to be a positive quantity. So we will go up, and we expect to see a local minimum. Similarly, if h is negative definite, if the Hessian is negative definite, then whatever perturbation we pick will give us something that is negative overall, which means we will go down a little bit. So that will give us our local maximum. That will allow us to construct the disk in which everything is less than f. The next proof is just going to be doing that properly, and in fact we aren't going to prove that probably until next week at the start of the lecture. For now we're going to take it as a given, and we're going to say this hand-wavy proof sketch is enough. But we are going to come back and actually prove this later. So we'll prove the classification theorem, but for now we're going to do some examples and take it as a given. Okay, so let's start with our old friend, this thing. And let's now classify these critical points and show that they do, in fact, meet the criteria. Before I move on, it is possible that you have met another criteria that is used for this classification. If you have, I will, in a moment, address that, and you should hopefully come to the agreement that they are the same criteria in different clothes. So we'll talk about that in a moment. For now, we'll just use what we know, and we will classify our critical points. We had a critical point at 0, 0, at 1 over root 2, 0, and at minus 1 over root 2, 0. And we worked out all the first derivatives. Let's do the second derivatives. D squared of f is equal to 2 minus 12x squared, 0, 0, and minus 2. So fxx, the two cross derivatives, fyy. fxx, fyy. Okay, so evaluate this at 0, 0 is equal to 2, 0, 0, minus 2. What are the eigenvalues? Yell them out. 2 and minus 2. It's a diagonal matrix, so the eigenvalues are the diagonal entries. What a convenient question. Lambda 1 is 2, lambda 2 equals minus 2, so this point is a saddle. And sure enough, that's exactly what we found here. There is a direction we can go up, there is a direction we can go down, so that all checks out. The second derivative of f of, let's do these both at once, plus or minus 1 over root 2, 0, is equal to, well, x only appears as an x squared, so it doesn't change anything, minus 4, 0, 0, minus 2, which means that lambda 1 is equal to minus 4, and lambda 2 is equal to minus 2. So this is a local maximum. And of course, that is exactly what we found by shoving this into Mathematica. looking at it and seeing that that is clearly a saddle and those are clearly local maxima. So math appears to work. That's good. Let's do an example where things go slightly wrong and look at how we can actually adjust around that. Just like in first year when you do an example where the second derivative test fails, we'll do an example where this classification is inconclusive. We have this here. Now this is a relatively innocuous looking function. Doesn't seem like anything could go wrong. The gradient, which is gx is equal to 3x squared minus 3y squared minus 6xy. I'm going to trust you can calculate these now and just write them out. x naught y naught is equal to 0, 0. So the only place where that thing is 0 is either x equals 0 or y equals 0 from the second thing. And from the first thing, if x is 0, then y is 0. I'm so sorry. And if y is 0, then x is 0. Okay, so we like a good algorithm. We have a series of steps to follow. Let's construct our Hessian. D squared of f of xy is equal to gxx, gxy, gyx, which is the same, gyy. And you go and calculate that because you're all very dedicated, and you get 6x minus 6y minus 6y minus 6x, which tells me that at the critical point, I get the zero matrix. The zero matrix is about as degenerate a matrix as it's possible to have, and of course its eigenvalues are, it has two eigenvalues that are both 0. Well, one eigenvalue, multiplicity 2, right? Lambda 1 is lambda 2 is 0. The test has failed us, but we are clever mathematicians, and we can go, well, all I'm doing is I'm looking for some way of getting a value that's less than 0, the value at 0, and some value that is more than the value at 0. So what we can do is just try some cross-sections. So I'm just going to say, well, what happens if I just let y equals 0? So instead of looking at an entire disk around my point, I'm saying, well, I'm going to try my luck and say if I just go this way along y equals 0, I should hopefully find something that tells me the answer. And I will, because this is a well-designed question. So if I let y equals 0, I get g of x0 is x cubed. So along that line, here is my point 0, 0. In the negative direction, I get x cubed 0. And in the positive direction, I get x cubed 0. So here I get f of xy is less than 0. And here I get f of xy is greater than 0. Which means that I can find points in my disk that are less than the value at 0. I can find points in my disk that are more than the value at 0. So since any disk must therefore have positive and negative values, because if I take that disk, I'm probably looking at something like this. It catches part of the negative side, it catches part of the positive side. What I have is a saddle. So when in doubt, just kind of pull your function apart to see if you can find it. There is no definitive algorithm that is the quote-unquote right way to pull it apart. A little bit of geometric insight is often helpful here. Yep.
For a shape like this, it would be like, think of it like sort of four shape, like four sides. Three of them would be going down.
Yeah, well, no, actually you'll get 3 down and 3 up. So this is actually, you'll see an example of this in the computer worksheet. This is kind of a twisted version of what we call the monkey saddle, which has space for the legs and the tail. You'll see a picture of that later. So I'm going to keep going because I don't want to get too sidetracked, but yes, the geometry has 3 down directions and 3 up directions. Okay. So sometimes this is taught as testing the discriminant of some value called the discriminant, where they said fxx fyy minus fxy squared. So you might have seen this before as the second order classification test. Then you do tests on D and fxx, which tells you whether you have a local maximum or a local minimum or a saddle or inconclusive. But what you're doing when you do this, if this is what you learned, is you are doing the eigenvalue test. These are the criteria that tell you the signs of your eigenvalues. It makes sense. The discriminant is related to the determinant of our matrix, and fxx, the sign of that, will tell you whether you have landed in positive or negative definite territory. So these are the same thing. I'm not going to show this. You might want to. But the problem with this is it does not generalize to n variables in a particularly nice way. So if I have something which has n variables, something like h of xyz is equal to xy plus xz plus yx, I can find the critical points easily enough. Y plus z, x plus z, x plus y, which has a single critical point at 0, 0, 0. Nice and easy to calculate. Linear system, full rank, easy to solve. So now we have the Hessian. And we need to understand how to construct a Hessian for more than one variable, and it is very, very easy. You've just got to put the cross derivatives in the right place. So hxx, hxy, hzz, xz. So the second thing changes along rows. hyx, hyy, hyz, hzx, hzy, hzz. And you can see that, again, this is symmetric. And in fact, for our function is 0, 1, 1, 1, 0, 1, 1, 1, 0. And now this is just a game of finding the eigenvalues. So the eigenvalues, for those who might have forgotten how we calculate this when our matrix is not diagonal, 1, 1, 1 minus lambda 1, 1, 1 minus lambda, determinant of thus, which is equal to 0, which if you expand it out gives me minus lambda cubed, plus 3 minus lambda squared cubed, plus 3 lambda plus 2 equals 0. Or, because we're all very good at factorizing, lambda plus 1 squared, lambda minus 2 is equal to 0. So our eigenvalues, should have given myself a little more room, I have lambda equals minus 1, plus 1, and plus 2. Negative, positive, positive. My eigenvalues have different signs. This is neither positive definite nor negative definite, so there is a saddle point. You couldn't do this using the test from the previous page. Yep. 2 minus 1s, thank you. Minus 1 with multiplicity 2. Minus 1 plus 2. Thanks. And we get our answer. So this is a saddle, but in 3 dimensions. A little harder to visualize, but if you just remember the definition, there is a disk, in this case a ball, and you can find directions where the value is positive and directions where the value is negative. Then the meaning is clear. Yes, I have time for a question.
So we do this and it's indeterminate. Then we have to do it in 2 dimensions. And like,
If you do this and it's indeterminate, it's a little bit harder to start constructing cross-sections, but honestly, you don't even have to do 2 dimensions. You can do 1-dimensional lines and hope for the best. When you have an indeterminate situation, you're kind of improvising. You move from classical music to jazz. All right, on that note, which makes me sound classy and cultured, I will see you all tomorrow. Just one thing, which is that the weekly quiz has opened, but it does contain content from this week. To reiterate, you get 3 chances, an hour to do 5 questions, and it will tell you which ones you got wrong. You cannot not get 100% on this. I will be so sad if the class average is not 100%. I'll see you all next tomorrow.
defining the local maximum and minimum using the disk? Does it matter whether the disk is open or closed? Or
It doesn't matter. Normally we use open C. In math, we tend to use open C when possible because when boundary becomes an issue, it has neighbors.
every point has
Every
neighbors?
point in an open set of it does not matter for our
Thank you.
Yes, sir. Thank you.
Probably later after this final Q&A. This last tutorial is actually Yes. Okay, great.
Well, I've seen it, I don't know.
Sure. What it means is that the difference is bounded by some constant multiple of h. So, big O notation is essentially saying if I have okay. Alright, I'm just going to put it here and then remember to do it. If I have something big, if I have f of x is say big O of n in some limit, so it's always n. What it means is that the absolute value of f of x so, right, no, I've done this wrong. Let's do this right. If I have f of x is equal to g of x, f of x, g of x plus order n. What that means is that the absolute value of f of x minus g of x is bounded by some constant that doesn't matter times 1. And it's typically in some limits, so as n becomes large, that means that the difference will not be like n squared or n cubed. Some limit on how different they can be. So what we tended to find in ours is that we have, say, order h as h goes to 0. What that means is the difference between f of x and g of x is less than some constant times by h. So as h goes small, that difference is squeezed out. So what this basically means is ignore all the stuff that's left in small h limit. G is bigger than anything that's. So in this case, what it means is that this thing, because this is the thing we care about, everything that's past it is smaller than the norm of h squared. But this is the norm of h squared. Is it the h? So basically, as h goes to 0, these go to 0 faster than this, so they vanish. It's a way of talking about limits, but with a little extra, but with a bit of extra information. Instead of just saying it goes to 0, how it goes to 0, which is actually quite important in a lot of applications. And it's like my whole research. But yeah, so order notation tells you how things approach the limit, and it kind of gives you a rigorous way of determining. Because this thing is k times h. Outside. So this thing is going to be smaller than k times h squared. So as h goes to 0, this goes to 0 faster. All of the non-cultural stuff learned first, which means this is the dominant behavior. And the smaller h is, the more dominant that thing is. That's the 1 minute clip notes. It's not a terrible thing to get to know, not just for this class, but for math in general. Order notation becomes extreme.
Yeah, I'm already seeing it in stuff that I'm doing. I'm physics.
Good.
Yeah.
Physics is all about order notation and throw away what you don't care about. As you have learned already. Well, it's good stuff. I hope that helps.
Yeah.
If you have more questions, your tutors should know this.
Sure.
So if they can't answer it, tell them in there.
Okay.
Take it easy. Nice to meet you.